Viitorul e al tău, noi punem temelia. UTCP, construim pentru România. UTCP, Universitatea de Construcții București.
Thank you very much for your kind introduction. Good morning, ladies and gentlemen. I am Mitsuyoshi AKIYAMA, professor at Waseda University, Tokyo, Japan. So it's my great pleasure to be here and to talk about toward life cycle reliability, risk, and resilience-based design and assessment of bridges and bridge networks and multiple hazards. Very long title, emphasis on ground motion, tsunami corrosion, and climate change. So this is a research based on the collaborative study with Professor FRANGOPOL at Lehigh University, USA. Unfortunately, today he is not here because he will deliver the keynote presentation on Wednesday in Timisoara. Yes, now he's there. So I will make a presentation on his behalf. So first, I want to introduce how I have been working with Professor FRANGOPOL since 2008 for more than 15 years. So you can imagine how the time is passing based on the amount of my hair. So, so first picture is taken in 2008. Since then, I have been working with FRANGOPOL in Endowed Chair Life Cycle Association. AKIYAMA is a bridge maintenance, and ASC SEI Technical Council on Life Cycle. So he often come to Japan, and we had a very nice dinner with my family, my wife, my boy, and also I went to his super big house in the US. So today it's my great pleasure to introduce what we have been doing. So Professor Kusunoki and Professor Hisada mentioned we have had so many disasters in Japan. So I graduated from Tohoku University in 1995. So since then, we have had so many big large earthquakes with the moment magnitude of larger than 6.5. In Japan, we believe if moment magnitude is larger than 6.5, we say it's a big earthquake. So some infrastructure may have damage. So you can see, so we have had so many big earthquakes since 1995. So my bachelor, my master, and my PhD, all research theme is seismic features. So I have conducted many experiments with the students at the Tohoku University. So after getting my PhD, I worked as a research associate, assistant professor, and associate professor. So I did many seismic experiments and computations. At that time, I strongly believe my mission is to contribute to developing more safer and sustainable cities against big earthquakes. But I made a big mistake. In 2004, as you know, Indian Ocean tsunami occurred. So more than 200,000 people were killed. At that time, Tohoku University has a very unique research institute of tsunami. If my understanding is correct, so at that time there are only two research institute of tsunami. One is located in Tohoku University, the other is located in Hawaii. So Professor Shito, I remember, Professor Shito asked me, why AKIYAMA you only focus on ground motion? You also need to study about the design of bridges and infrastructure against tsunami. But as I mentioned, at that time, I strongly believed my mission is to do research on seismic issues, seismic design. So I didn't care about it. So in 2011, Great Japan earthquake occurred. So at that time, I was still associate professor at the Tohoku University. I was working with Professor Hisada. So I often took my son, Ryuzo, to the park near Sendai Airport. So he really enjoyed this park because he can see airplane, and also this park is located very close to coastline, so he can see Pacific Ocean. So you can see, this is a slider he enjoyed. So all the facilities are completely destroyed. So this is Sendai Airport. So I made a very big mistake. So I thought, yes, my research theme is to study seismic design or seismic assessment of performance of bridges. But in Japan, we have so many other disasters. So it's meaningless. We have to protect our infrastructure from all natural hazards. So since then, I try to expand my research field. So fortunately, as I mentioned, I began to work with Professor FRANGOPOL since 2008. He's a really specialist of multiple hazard. He encouraged me to study, to expand my research field to include more other disasters. So Professor Hisada already introduced his office. Also, this is my office at the Tohoku University. And this is a building including our office. So this building was completely destroyed and demolished. So it's funny because I was teaching seismic design of concrete structures in this building. So then I realized, I'm not qualified for teaching the seismic design of concrete structures. Anyhow, so and then I moved to Waseda University in 2011. So I will introduce some lessons from 3 big earthquakes, including the 2011 Great Japan earthquake, 2016 Kumamoto earthquake, and 2024 Noto Peninsula earthquake. Some pictures are overlapped with Professor Tsunoki, so I will skip some slides. So you can see this is a Fazlur overpass bridge, completely collapsed due to ground motion of the 2016 Kumamoto earthquake. So this collapse prevented the traffic passage of Kyushu Expressway. Actually, this is a local overpass bridge and not so important for local community. However, once the overpass bridge collapsed, this can prevent the traffic passage of highway, expressway. So we have to prioritize the seismic retrofit, considering this point importance. Also, this is a bridge pier damaged by 2016 Kumamoto earthquake. So you know this bridge was retrofitted using reinforced concrete jacketing. So because highway is a very important infrastructure in Japan, so they already conducted the seismic retrofit. However, as you know, once we provide additional lateral strength to bridge pier, So now bridge pier is not lowest capacity among the bridge elements. So then, during the 2016 Kumamoto earthquake, so Fujin and pile foundation has had damages. So we see very serious residual displacement. It's very difficult to do seismic retrofit appropriately. We have to make a balance of structural capacity among all bridge elements. Also, this is pictures taken before and after 2011 Great East Japan earthquake. So you can see the concrete color is different because this bridge pier was also retrofitted using reinforced concrete jacketing. This seismic retrofit could prevent the damage from ground motion. However, this couldn't prevent washout of the superstructure. Also, this is Koizumi Bridge. Koizumi Bridge has a superstructure supported by 5 RC bridge piers. One bridge pier was completely destroyed due to tsunami. And also, so during the field investigation conducted after the 2011 Great East Japan earthquake, I couldn't see the superstructure of Koizumi Bridge. So, where is the superstructure of Koizumi Bridge? I walked, and finally I found the superstructure. And I measured the distance, so from the original position, and it was 400 meters. So tsunami washed away the superstructure more than 400 meters. So tsunamis are really strong hydrodynamic forces. This picture was this picture shows Ukai Bridge taken after the 2024 Peninsula earthquake. So as you can see, this bridge is a skewed bridge, right? And there are 3 pedestrian bridges, but 2 pedestrian bridge was destroyed, probably due to rotation of superstructure by ground motion. However, this one, there is no pedestrian bridge. Where is this one? Yes, here. Oh no, here. Yeah, so this one was washed away due to tsunami. So this bridge had multiple actions. First, ground motion, and second, tsunami. So in Japan, if a bridge is located near coastline, we have to consider effect of not only ground motion, but also tsunami on the bridge performance. Also, during the field investigation conducted after 2011 Great East Japan earthquake, I found many infrastructure and concrete structure deteriorated due to corrosion. So in this region, during winter, they use a lot of de-icing salt. Also, in Japan, there are many coastlines. So due to airborne chloride, so concrete structure deteriorate. So we have to evaluate structural performance considering the effect of material deterioration. So it's quite difficult to present the solution for giant tsunami. As I mentioned, so giant tsunami can give very strong hydrodynamic forces, and the superstructure is washed away for more than 400 meters. What is the solution? So it's quite difficult, but based on my experience of field investigations, I could say rigid frame is one solution, because I only saw one collapse of rigid frame. So you can see here, this bridge was affected by ground motion and tsunami, but almost no damage. Also, this is the Asochoyo Bridge, and the Asochoyo Bridge was affected by fault movement, displacement. And this bridge pier was displaced due to landslide. But without the support of abutment, rigid frame is stable. So local government simply remove this abutment and they reconstruct the abutment, so this bridge could contribute to recovery process. So this may be one solution. So let me now introduce what we are doing based on these lessons from past disasters. So here is Japan, and now I focus on Kochi Prefecture. Kochi Prefecture is facing to Nankai Trough. So Nankai Trough is a really big concern. It may be expected that economic loss and damage to structures and infrastructure systems may be larger than those from the 2011 Great Japan earthquake. So we have to prepare for this big earthquake. And also, you can see this bridge is located near coastline, and a very high temperature and very high humidity. Here is a very dry, so I need water. So. Okay, so now in my research team with FRANGOPOL, we are always see the bridge networks. And of course, sometimes we focus on individual bridge, but the most important part is bridge network. How to ensure the functionality of network subjected to multiple hazards. I will give you some ideas. So now, as I mentioned, in Japan, we have to consider seismic and tsunami hazard if network is located near coastline. So bridge, seismic and tsunami hazard can damage to structures and infrastructures. So we have to quantify the risk and resilience. As you know, transportation network plays a crucial role, right, in the evacuation of affected people and the transportation of emergency goods and materials. So what is the most troublesome obstacle? So I believe one of them is disaster waste. You know, seismic and tsunami disasters always cause a huge amount of disaster waste. With the disaster waste, we cannot proceed the recovery process. We have to remove disaster waste. This is a very serious issue. And also, as I mentioned, if a structure is located near coastline, we have to consider the effect of airborne chloride on the deterioration of materials. So proper modeling of structural systems for its entire life cycle, considering the time variant load and material deterioration is needed. Also, when we discuss the time variant loading, now climate change is a really serious issue. So global warming could change the location of coastline, and also global warming could increase the sea level rise. So this is a very difficult issue, like non-stationary sea level rise and no-person seismic actions. But anyhow, intensified tsunami could cause more disaster waste and could damage more structure and infrastructure. And also global warming may accelerate the deterioration of the material. So we have to consider all the disasters and natural hazard. And also considering we have to know how global warming affects the functionality of road network. So when we do research, we always consider 4 performance indicators: risk, resilience, reliability, and sustainability. With core technology such as machine learning. Now machine learning is a really powerful tool, and also numerical simulation such as finite element modeling, also spatial modeling, and experiment to understand the real phenomena. So I will introduce some research activities based on these 4 performance indicators. So first is the resilience of infrastructure systems under multiple hazard. So this is a really traditional topic. So which bridge should be retrofitted first? So based on the risk estimation and based on the resilience quantification, we could identify which bridge should be retrofitted. But also we have to now care about which is more important, seismic retrofit or maintenance of deteriorated bridges. This is also, this should be considered now when we prioritize the retrofitting actions. Also, this is my dream. I really want to, as I mentioned, the bachelor, master, PhD. My thesis is always presenting the seismic issues. So I want to present an idea of damage-free, even subjected to very strong earthquakes. So now I'm really interested in friction pendulum system. Now we can use 3-dimensional printers. So with 3-dimensional printers, we can make a very complicated structural shape, but very cheap, not expensive. So with friction pendulum system, we can increase the seismic performance more. But in addition, for ground motions, we have several ideas, but as I mentioned, for tsunami, it's a too severe, too much size, it's a too much strong action, right? So now for this kind of very catastrophic event, now we are saying we have to have an idea, assuming the collapse of bridges. So one idea is ABC concept. In the US, they have this concept, accelerated bridge construction. They introduced this concept to save the construction time on site. But also, this concept can be introduced to a location with a very high natural disaster hazard. Right? Assuming the collapse of bridges, we can present some idea how to reconstruct the bridges. And this can be used as a temporary bridge, which can contribute to the recovery process. Also, I want to introduce some activities on tsunami hazard assessment concerning the effect of sea level rise. Now there are several mathematical models to quantify seismic tsunami hazard, but if we have to combine effect of sea level rise, this problem is really complicated. So now my student Abdul Al-Hamido developed a procedure to quantify the probabilistic sea level rise hazard. So once we determine the time T1, we can evaluate sea level rise hazard. Then we conducted the tsunami propagation analysis. Now we can use GIS and we can obtain information on individual structures. So we can obtain the inundation depth due to tsunami. So combining sea level rise hazard and tsunami hazard, we can obtain the new tsunami hazard curve. So we repeat this process like from now on to 2100, we can have new hazard curves. So this hazard curve can be applied to evaluate the bridge failure due to tsunami. So now we can estimate for next 100 years. So failure probability due to tsunami is blah blah. We can say it. However, the problem is more complicated, right? Because before tsunami arrive, ground motion come. So we have to evaluate tsunami fragility, considering the effect of damage to bridge due to ground motion. So actual process is seismic wave first, then we have to consider tsunami effect. So fragility curve should be revised considering the effect of damage to bridges. So now my PhD student, Aoki-kun, developed some new model to evaluate the reliability of a bridge considering seismic and tsunami hazard. Also climate change. It's a really complicated process, but the important point is in his method is he tried to evaluate connectivity considering the damage of individual bridges. So this is a whole procedure. So if you are interested in this topic, connectivity assessment of road network exposed to multiple hazards, seismic and tsunami hazard. So he applied his method to real road network in Mie Prefecture, facing to the high hazard of seismic and tsunami. So using his method, so we can evaluate the network connectivity. So and we can identify which hazard is more important. What we should do to increase the connectivity of road network even after seismic and tsunami events. I used so much time. So now still mission 2, but I will accelerate. Okay. So next one is a maintenance topic. As I mentioned, if a bridge is located near coastline, so bridge performance deteriorate. So Professor Dan Frangopol presented this relationship between performance indicator and time after structural construction. So based on many experiment and computational researches, now we know the basic process of deterioration. So if chloride content is larger than the threshold at the river, still corrosion begins. And due to expansion of the corrosion product, we see the cover cracking. But still, we cannot say if this is a bridge damaged by chloride attack. So from this picture, we still cannot answer to these two very simple questions. How long can we use this bridge? How much does the bridge performance deteriorate? So I believe corrosion crack width is a very important indicator to understand the level of deterioration of bridges. However, it's not so easy to evaluate actual steel corrosion based on the corrosion crack width. Why? As shown in this picture, there is a very large, huge uncertainty associated with the crack width and steel weight loss. So for this problem, I and Professor FRANGOPOL presented a new framework to evaluate the load-bearing capacity of deteriorated concrete bridges just based on the information of corrosion crack width. So this process includes experimental part, stochastic simulation, and FE modeling, machine learning, and finally probabilistic prediction. So today I don't have enough time, I will present outline. So once we obtain the corrosion crack width distribution, we can use machine learning to predict the steel weight loss distribution inside concrete. But we have to know there is a very big uncertainty, so we have to take a probabilistic approach. So we repeat finite element analysis, and finally we can obtain PDF, probabilistic density function of flexion resistance. So this is a simple case study using 6-meter RC beams. So we use a drone to take corrosion image associated with corrosion cracks. And based on this digital image, we can get the corrosion crack width. So this is a real picture of corrosion cracks. So you can see, if we take a picture very close to RGB, the image is very clear. But if we use a drone, so it's not so clear because drone is not sometimes not so stable, and also bottom of RGB HPI is not so bright. So you can see the difference of image quality. So we conducted the loading test to know the actual maximum load, and we compared how our PDF is close to experimental result. This is a result, and the red line shows the experimental result, loading test result. So mostly, if we can have a very clear image, so our PDF mean is very close to loading test result. It's fine. However, if we estimate a PDF based on images taken by drone, so it's really overestimated because the image quality is not good. So if we use image of corrosion cracks taken by drone, so almost no corrosion cracks. So flexural capacity is overestimated. Very sorry. So this is the last mission, mission 3. So now in international association, there are many research activities on climate change in the field of structural engineering. So in IABSE Commission 6, IABSE has 6 commissions, and Commission 6 is, the theme is sustainability. Now I'm chair of Commission 6, and the vice chair is Professor Lehigh University. And also ASCE has a technical council on life cycle performance. The founder is Professor FRANGOPOL, and now current chair is Professor Fabio Diondini. And both these activities are focused on how to affect the climate change on the structural performance. This is a main target. But as a structural engineer, I want to contribute to stopping the global warming, because the concrete industry has so many CO2. So I want to reduce the total amount of CO2. So my colleague, Professor Nakagaki at Waseda University, developed a very interesting idea. He can make a new powder from CO2 and seawater. And this is a powder. It's not calcium, it's a magnesium. But you can see almost it looks like a concrete, right? Only from CO2 and seawater, we can make new concrete. It's a really carbon negative concrete. So now we try to make some new product, but at this moment we face a very difficult issues because this concrete is made of seawater. It includes too much chloride content. So, but in the future, we try to apply this concrete to infrastructure. I'm sorry I talked too much, but I and Professor Dan FRANGOPOL want to work toward a safer, more resilient, and sustainable infrastructure systems. So I would like to thank all my colleagues and my past and current students. So thank you very much.
Thank you very much, Dr. AKIYAMA.
Viitorul e al tău, noi punem temelia. Construim pentru România. Universitatea de Construcții București.